Hello everybody, tonight or this morning, it's currently Wednesday morning, I'm going to be discussing how to tackle Champak's challenge question number 1 from yesterday's maths lesson, 12th or 11th of August. I don't really know the date, doesn't really matter. Right, off we go. Now, it asked to prove that a to the fourth minus 1 has a factor 16 when a is an odd number. Now, to do this, we're meant to be using the method of induction, which follows the set of orders, which is tape, involving a trial to assume something to prove and then explain it. Now, what we want to do to try this is we want to arrange this into an equation. So what you really want to do is have a to the fourth minus 1 equal 16 times some other value. Let's give it a capital B. So a to the fourth minus 1 equals 16 times b, because that would be 16 times a value equals a to the fourth minus 1, which is by definition what a factor is. Right, so this b value, to be a factor, it has to be an integer. It can't have any decimal places, so the b value has to be in the set of the integers, which we represent by this z, and you can also draw the z with that little fancy line down there, but I prefer it with a line through. It doesn't make too much of a difference. I think on the test you should do it like that, but I can't be stuffed, it's too late. And a in this case has to be odd, but to define an odd number, I'm going to use the odd number equation, which in this case I'm going to define a as equal to 2k minus 1, where k is in the set of the positive integers, because I forgot to mention up here, is positive odd number. So because it has to be a positive number, we can get any positive number, for example 1, take this in, so if we set k be 1, then k is 1 in this scenario, so 2 minus 1, and that's going to come out as 1, so a is equal to 1. And that's going to be the first number, and as we increase k, 1, 2, 3, 4, we're going to get the odd numbers of 1, 3, 5, and 7. Now, this information can help us create a system where we can use k plus 1, because we can move in standard increment steps of k, instead of having to jump around with bigger gaps. Right, now we've got this underway, let's crack into the try section of this. Alright, let's try when k in this case is going to equal 1, which is going to let a, naturally, a will equal 2 times 1 minus 1, and we just discussed this, that's going to equal 2 minus 1, which is just 1. Right. In the case where a equals 1, we can substitute it back into this equation over here, and then 1 to the power of 4 minus 1 equals 16 times b. And that's going to be 1 to the fourth. It's just 1 minus 1. It's going to be 0. 0 equals 16b. And yeah, if b is 0, that checks out. Done. That works as a trial. But it wasn't a very rigorous trial, substituting it in, because we got one of our sides equaling 0. So we can do another trial. There's nothing against doing that. If you want to, it's not a bad move. Alright. So let's move down a square, and let's go and try k equals 2. And let's plug that into it. So in this case, we'll get our a value to equal 2 times 2 minus 1. That's going to be 4. Minus 1 is going to come out to be 3. So a is going to equal 3 in this case. So what we get over here is equal to 3 to the fourth minus 1 equals 16b. And that's going to be 81 minus 1 equals 16b, which we can get as 80 equals 16b, And because 80 is 5 lots of 16, we can go as equal to 5. And yes, because 5 is a integer, it has no decimal points, and is a real number, it works, and this solution does check out. Alright, so now that we've tried it for some numbers, we can move on to the step of an assumption. Let's assume that we have a to the 4th minus 1 equals 16b. B is in the reals. B is in the positive, is in the integer set, and a equals k, 2k minus 1, and k is a positive integer. Because of this, we can start working our way through the proof. Now, we can substitute this back into our value of a there, so we can have 2k minus 1 all to the 4th minus 1 equals 16b. This is still part of our assume step. We're creating some assumptions we can work off of. So if we ever see this in our equation, we know that we can replace it with 16b, which will come in useful because this doesn't have a very clear solution, and that's why we're assuming it to be true. So from this, it might be useful to show the expanded form of it. So we can take that out and expand this into, well, 2 to the power of 4, which is going to be 16 times, well, the first row of Pascal's triangle, because we can go excess of 14641 will be this row of Pascal's triangle. And that's just from binomial expansion. You can look into that in the textbook if you don't know how I'm getting these numbers. But just to do it quickly, k to the 4th, and that's going to be, well, 2 cubed, so it's going to be subtract, because we're going to have minus 1 getting in there 1 time, and that getting in there 3 times. So this is going to be minus 8k cubed times our constant value 4 for that spot. Then we're going to have this coming twice and a negative number squared, so we're going to have positive 4k squared times our constant 6. Then we're going to have minus, again, because we're going to have an odd number of our negatives. So we can get a 2k, just one of our first term, multiplied by 4. And then finally, we can add on our 1, which is our minus 1 cubed, which then simplifies down to 16k to the 4th minus 32k cubed plus 24k squared minus 8k plus 1. So we know if we ever see this anywhere at all, that was a terrible underline, in our equation, we can resubstitute it in to 16b, because these are still equivalent. Alright, so with those assumptions out of the way, we can start moving on to the proof step. Proof. And to prove it, we're going to see if we can substitute k plus 1. So you know how before we had a equals 2k minus 1? We're going to jump k plus 1 back in where k was. So our new equation is going to be a equals 2 times k plus 1 minus 1, which equals 2k plus 2 minus 1, which equals 2k plus 1. Now if we take that back to our original equation of a to the 4th minus 1 equals 16b, then we can get 2k plus 1 all to the 4th minus 1 equals 16b. Not too hard. Now, from here, we can start expanding this out. So, using our similar expansion as before, we're going to get 16k to the 4th plus 32k cubed plus 24k squared plus 8, I think 8k, check it against what we had before. Notice this is almost identical to what we had up here, but these terms here and here are positive. In this case, because we don't have a -1 in the brackets, we have a +1 there in the brackets. And that's what the main difference between this and the previous one are. Now, substitute that through, and we're going to have -1 on the end equals 16b. And you know what? Let's just work with the left-hand side of the equation. And this is going to be the right-hand side, naturally, over here that I've just written down. That's left, that's the right there. Now, let's just work with the left-hand side of the equation, because this makes things easier and you don't have to write so many equal signs. So what we want to do is we want to be able to start factorizing this down. So what we want to be able to do is get this term out of it, get from what we had in our assumed step, 2k minus 1 to the 4th minus 1 as equal to 16b. Oh, I've made a mistake there. That -1 also carries through, so that also has to be -1 there, -1 there on the end of each of these. So if we can find that anywhere, we know that we've got 16b. Right. So to get that, we want to get this to have the terms -32k cubed and -8k. So what we're going to do to get these terms in is we're going to add 32k cubed and subtract 32k cubed. Because we've added and subtracted the same term, this hasn't changed the value and thus kept the sides equal. We're going to add 8k and subtract 8k. This gives us the two terms. It gives this term and this term, which are the terms we're looking for. Now we can reorganize this and move these terms across to the left to get 16k to the 4th minus 32k cubed plus 24k squared minus 8k plus 1 minus 1. And then our remaining terms that we're moving across, let's get a nice orange, 32, the 8, this 32, and this 8. And they can come across to the right here, and we'll get plus 2 lots of our 32k cubed. It's going to be 64k cubed, and plus another 16k. Alright, now this term on the left, since we've got it now matching what we have up here in our assumed step, we can factorize back down to 16b, because this compresses all into a nice lot of k minus 2k minus 1 to the 4th minus 1, which means our next line of this equation can show the compressed form of this, which is 16b, because we know that this equals 16b from our assumption, and then we're going to add on to the end of that 64k cubed plus 16k, which, if you notice closely, we all have these 16 terms involved. So you can take 16 common out the front and leave b plus k cubed plus k inside those brackets. And what we've got is 16 times a value, which our right hand side, when we were doing this proof step, we were meant to get equal to 16a, because we're not going to have the same factor as we did before. So that's 16a there, and that's our right hand side equation. So we can bring the right hand side back in over here. Here comes the right hand side, back in we go. It's just kind of gone off the page, and here it's coming back. And it equals 16a. And because we can cancel 16s off both sides, we know that a is going to involve b plus k plus another k, or k cubed. And because these k's are both positive integers, and b we know is an integer, and because the sum of three integers is going to be an integer, because there's no decimal points anywhere, we know that a is going to be in the set of the integers, which means, boom, this step is checked out, and we've got a really nice way to go. Now I have to do the explanation step, and this is one of the steps I'm shakiest with, so I probably won't go too much into depth. So it goes along the lines of, therefore, since a to the 4 minus 1 equals 16b, or has a factor, let's write it fully, has a factor for a is equal to, we can go 1 or 3, 1, I'll write both a equals 3, a equals k, and a equals 2k minus 1, and a equals 2k plus 1, therefore a to the 4 minus 1 has factor 16 for a equal to k, or a equal to 2k minus 1, with k in the set of the positive integers. From in math process of mathematical induction. And that should be done. Alright, I hope that was useful. And remember, if you didn't solve this the same way, your solution is still valid. It's just a different way of getting to the answer. And as long as you follow the rules of a proof, then it's not wrong. It's probably more useful to have multiple different proofs that show something similar. Alright, see you.